Good morning, good afternoon, good time zone, wherever we may find you. It's my pleasure to welcome you to this Sunlight Reflection Briefing. My name is David Biello, and I'm the Science Curator at TED. And I am very excited for today because we get to learn about a technology that could help save us from global warming. And I guess I should open by saying it's bad out there when it comes to climate change. We're in a crisis and we have a responsibility, but it's also an opportunity to create the world that we want. And that's what these technologies could allow us to do. And that world that we want, or that I want anyway, includes a stable climate. And so hopefully we can come together today to learn about the opportunity to build that world we want. Now, it's also my great pleasure to introduce one of my co-hosts for this event, the inimitable Kelly Wanser, who is the executive director of SilverLinings, a organization dedicated to stabilizing our climate in the next decade. She's also been a leader in this space, both domestically and internationally, working with the US Congress, the US National Academy of Sciences, the United Nations. Please join me in giving a big welcome to Kelly Wanser.
What we'll describe very powerfully are the risks associated with the first order problem we have of heat stress on natural systems. This heat stress operates a bit like a fever on the human body. So as that fever rises, systems can start to break down, leading to exponential changes that must be prevented to ensure safety and to prevent the permanent, widespread destructive changes to natural systems. Today, our exposure to that risk from SilverLining's perspective is unacceptably high. And so I'm going to talk to you a little bit about what that means and how it translates. So as I mentioned, this heat stress is the first order problem that's created by greenhouse gases. And so we need to think about in the very near term whether there's anything we can do to alleviate that heat problem. And where that sits in terms of the overall picture is that the current portfolio of solutions that we have to climate tend to unfold over many decades. So reducing emissions are forecast to really have a meaningful effect on heat in the climate system in the latter part of the century and beyond. It's possible that very large-scale efforts to remove CO2 could start to operate in a few decades, but these take time to build, time to study, and time to take effect on the climate system. So where we are today is that for responses to climate that have a very meaningful impact on heat energy in the climate system within 30 years, our portfolio is light and our cupboard is bare. And so from SilverLining's point of view, we think this puts us in an unacceptable position of risk exposure to near-term climate change. And what Will talked about, we have a lot of uncertainty as to what the climate system will do in the next decade, 2 decades, or 3 decades. And so we think that it's a very important part of our role, all of us here collectively together, to ensure that we have sufficient measures to provide safety to people and protection for natural systems. And so, looking at this in the context of IPCC projections in the high emissions scenario, we're kind of on the pathway that Will described. What we hope to do is aggressive emissions reduction, which still under current projections takes us beyond the realm of safety at 2 degrees, and certainly what people now think might be required is 1.5 degrees. And so it's been proposed that we need to do aggressive carbon removal. Many of you are involved in these kind of efforts. We are champions of those too. It's not our main area of advocacy, but we think they're essential, critical parts of the portfolio. What we don't like is the uncertainty that we have over which of those things will work and how rapidly they could be scaled. And so it leaves us with the need to, in this sort of COVID language, bend the curve. How do we ensure that we do not hit the point where the natural system starts to move beyond our control and contribute to the problem itself. Similar to, in COVID, when the problem becomes exponential and rho is bigger than 1. So there's a point where the natural system starts to contribute to climate change in a way that could outpace any human ability to respond to it. And it's very essential that we don't hit that point. And since there's uncertainty around that, we think it's very important that we have measures in place that allow us to respond quickly if we need to, if we start to see these things happen. And so one possibility that I'm going to talk to you that we're all going to talk about with you today is the idea of reflecting sunlight from the atmosphere. So scientists over the past couple of decades have looked at the question of if you needed to respond to climate change quickly, and particularly within a few years or a decade or two, what are the most promising approaches? And in 2015, the National Academy of Sciences in the United States did a study where they determined that the most promising approach is based on one of the ways that nature regulates temperature, and that is the reflection of sunlight from clouds and particles in the atmosphere. What you're seeing here is a NASA simulation of the movement of clouds and particles in the atmosphere. Scientists hypothesized that increasing this reflectivity by just 1% might offset a doubling of CO2 or several degrees of warming. And so that's the foundation for what we're talking about today. They base their hypothesis on observations from nature. And one of them is what happens when very large volcanoes erupt. When Mount Pinatubo erupted in 1991, it was sufficiently powerful that it pushed material all the way into the outer layer of the atmosphere, the stratosphere, where it circulated for a time until it fell back to Earth, and it produced a measurable cooling of the planet by about 0.5 degrees C for almost 2 years. And this was due to the reflection of sunlight from the particles directly circulating clouds in the outer atmosphere. This also led to a notable recovery of Arctic ice in the year after Pinatubo erupted. So you can see here in the ice record, there was this recovery, and then the Arctic ice receded again. So based on these kinds of observations, scientists and other scientists arrived at the hypothesis that there might be a way to produce this actively. And similarly, phenomenon observed in the cloud layer, what you're seeing here is the reflection of bright streaks created in the lower cloud layer off the Pacific West Coast of the United States. These streaks are created by the particle emissions from ships. And this effect is known as the cloud aerosol effect, and it's actually produced by the particulates in emissions, more of what we think of as the dirty particles, and the way that they mix with clouds that often has the effect of making them a little bit brighter. This effect is called the cloud aerosol effect, and it is producing a sort of cooling shield today that we don't understand fully. Scientists believe that this cloud aerosol effect, this slight brightening that our pollutants are producing, is leading to a cooling effect of somewhere between 0.5 degree and 1.1 degrees C. So while we have the warming of greenhouse gases, we have currently today a form of sunlight reflection that's created by human activity that is cooling the planet at scale that we don't understand very well. 2020 is producing 2 large-scale experiments in reducing this effect. In January of 2020, the IMO implemented regulations to dramatically reduce these particulate emissions from ships. This is really good for human health, but it may result in a reduction in this overall brightening that the ships are creating as they traverse the ocean today. Similarly, and at an even bigger scale, the reduction of aerosols associated with the reduction of economic activity during COVID is producing a dramatic effect on sort of the aerosol composition from pollution that may result in a measurable warming effect this year. Barrett from NOAA may talk about this a little bit later and how they hope to study this as a natural experiment. But this cloud brightening effect is related to one idea that scientists have had in terms of sunlight reflection to cool climate. And so they postulated that there might be a way to optimize this effect over the ocean using tiny particles of sea salt in a sort of cleaner, more natural way to brighten clouds in specific parts of the ocean where in doing that, you might actually create a global cooling effect. In fact, early model studies suggested that by brightening just somewhere between 10 and 20% of these marine clouds, which represent about 3 to 5% of the ocean surface, you might be able to offset a doubling of CO2. This effect is also localized and temporary, so scientists have postulated that it might be possible to use this type of effect to offset impacts in local regions. One idea is the possibility of brightening clouds in areas where hurricanes form to reduce ocean surface temperatures and thereby reduce the force of storms. This idea is very hypothetical. There haven't been any resources associated with studying this. Similarly, in a sort of regional way, there's the notion that you might use cloud brightening or related types of influences to cool ocean surface temperatures in a way that might help protect corals. And later on, folks will talk about a recent experiment in Australia related to this idea. These are very speculative, they're very early. Scientists really don't know whether or not they'll produce results, but they hope to study them. The more prominent idea in this category is the idea related to what very large volcanoes do when they go off, the dispersion of particles into the stratosphere to reflect sunlight directly. And scientists have a fairly high degree of confidence in this effect based on what they've seen with volcanoes. What they don't know as much about is what the longer term, medium and longer term side effects might be of this type of alteration of the composition of the stratosphere. And so that's what they'd like to study. But in terms of the potential benefits, what I'm showing you here is a simulation from NCAR. It's the first ever simulation using a global climate model with an overlay of a controlled ejection of particles into the stratosphere to produce cooling, starting in 2020 and moving through the end of the century. And this is a model comparison of conditions under the high emissions scenario, RCP 8.5, versus the scenario where particles are introduced to the stratosphere to produce cooling. And the results that you can see here is a marked difference in the surface conditions of the planet. So with this type of intervention, we're able to keep the surface temperatures of the planet relatively close to those of today. Without it, those temperatures become very, very different conditions for livability, survivability in ecosystems. But as I said, there are a lot of effects that we don't understand. And in order to understand and project what these approaches might do, involves actually improving our ability to observe and predict the Earth system. Right now, we are actually underinvested in the capabilities that we need for observations of the parts of the system that are most critical to these questions, including surface and aerial observations, certain space-based observations, and tipping points. And we are underinvested in climate model predictions and the science that goes with them to help us improve our ability to forward project what the climate system is doing for all of these kinds of questions. For these sunlight reflection interventions, those predictions are critical. And so this is kind of surfacing where our investment gaps are in climate research and climate forecasting capabilities in general. In addition to that, we need directed scientific research on these individual techniques. And so that's one of the reasons that we're here today, is to see how that research is emerging, where we might be able to catalyze it forward and catalyze it in ways that activates public sector money and complements public sector money. So this is a really exciting area. I'm excited to talk to everyone here on the phone because I want to emphasize that climate prediction and the climate system is the largest complex systems question on planet Earth. The only sort of bigger competing problem in bigger systems analysis problem is the entire universe, is astrophysics. So this is a hard problem. It requires computing resources. It requires complex systems analysis. It requires a lot of disciplines to work through. At the same time, there's low-hanging fruit to sort of catalyze this, move forward answers to key questions quickly. And this is starting to happen in different parts of the world. And so we have a number of research efforts in the United States that are relatively small and emergent, but at very prestigious institutions with some of the highest caliber people in the world working on these topics, and you'll see them here today. This category is also emerging in other parts of the world as impacts grow. And so we have in China, we have a directed effort at Beijing Normal University to look at the stratospheric interventions. China is also operating fairly large-scale weather modification activities that are related to this. They're sort of not the same, but variants. And what we're starting to see is that these activities to, inject clouds to increase precipitation over the Tibetan plain, like they're doing in China in the area the size of Alaska. The United Arab Emirates has a $400 million rainmaking fund. In Indonesia, just in January of this year, they shot particles into clouds offshore to induce rainfall to prevent flooding. So we anticipate that some of these localized and regional efforts may start to grow, and they may grow into the sort of notion that the real solution for some of these dire sort of circumstances is a sort of global intervention. And so there's also the notion here that we in the United States do not operate in isolation, and others in the world may start to explore these techniques. And so understanding whether they are in fact useful parts of a climate portfolio or sort of emergency response function, or whether we need to understand them in order to engage with others who may try them and may try them in ways that are unwise. We think both of those questions are really, really important and are drivers for what we're doing here. Ultimately, especially in the near term, this is a deep matter of social justice, and it may be important that we in the West take responsibility to prevent the most dire impacts from happening in the next 10, 20, 30 years. There's a recent study that said that as many as 3 billion people could live in unlivable places, or that the places that they live in could become unlivable by 2050. From our perspective at SilverLining, that's unacceptable. And it's our responsibility and our duty to make sure that we use all of the knowledge, technology, and capabilities that we have to keep the world safe for all of its people, especially its most vulnerable ones. So on that note, I'll say one of the lessons of 2020 that we've learned is the importance of science-based decision-making. And so for these questions, in terms of how we respond in the climate portfolio and whether we might be introducing technological capabilities as a response to some of the acute threats that we face, we need to prioritize science-based decision-making in these cases. And in order to do that, we need science. We have, as a people, done this very successfully. I have up here the Montreal Protocol as one example of an existential threat that we have addressed incredibly successfully as a world community following the science. And we're confident or hopeful that we could do the same thing here. In order to do that, we need quite a bit more science than we have today. In fact, scientists in the field think we have a decade of research to do just to assess whether or not you would invest to scale these sort of approaches, whether they belong in the climate portfolio. We're hoping that that can be accelerated maybe to a 5 to 7 year time horizon. So this is just the assessment research so that we can determine whether or not these things are viable solutions. Events may move faster than that. So everything that we do this year, next year, to catalyze this work has a really, really profound impact on what might happen in this field and indeed what might happen to climate.